Hello and welcome to my YouTube channel ChemWis. In this video, we are going to discuss a very important topic, that is the hyperconjugation. We will go through the following points: definition of hyperconjugation, examples, hyperconjugation from molecular orbital point of view, negative or reverse hyperconjugation, and significance of hyperconjugation. Let's start with the definition of hyperconjugation. Overlap of sigma orbital of sp3 hybridized CH or CC bond with adjacent vacant p orbital, partially filled p orbital, pi star or sigma star causes delocalization of sigma electrons and thus increases the stability of the system. This is called hyperconjugation, no bond resonance, or Baker and Nathan effect. Let's take one example of each case for better understanding. The first example is ethyl carbocation. This carbon is sp3 hybridized with 3 CH sigma bonds. This carbon bearing a positive charge is sp2 hybridized with a vacant p orbital. There is free rotation about the CC single bond. So, at a particular moment, one of the 3 CH sigma orbitals will be parallel to the vacant p orbital, which allows the overlap between that CH sigma orbital and vacant p orbital, and transfer of CH sigma bond pair to vacant p orbital and leading to the formation of H plus and alkene. Since there are 3 such sigma bonds, so there will be 2 more such structures formed by delocalization of 2 other CH sigma electrons. These structures are called hyperconjugative structures. Second example is ethyl radical. In this example, this carbon is sp3 hybridized with 3 CH sigma bonds. The carbon bearing radical has partially filled p orbital. Overlap of CH sigma orbital with partially filled p orbital allows the movement of one of the 2 sigma electrons to partially filled p orbital and thus leads to the formation of H radical and alkene. Since there are 3 such sigma bonds, so there will be 2 more such structures formed by delocalization of 1 electrons from 2 other CH sigma bonds. These structures are called hyperconjugative structures. The third example is 1-butene. This allylic carbon is sp3 hybridized with 3 CH sigma bonds. These 2 carbons are sp2 hybridized. There is a vacant pi star molecular orbital. CH3 can freely rotate about the CC single bond. So, at a particular moment, one of the 3 CH sigma orbitals will be parallel to the vacant pi star, which allows the overlap between CH sigma orbital and vacant pi star molecular orbital and transfer of CH sigma bond pairs to pi star. When the pi star is filled, the pi bond is broken. This leads to the formation of H plus and allyl anion. Since there are 3 such sigma bonds, so there will be 2 more such structures formed by delocalization of 2 other CH sigma bonds. These structures are called hyperconjugative structures. The next example is 1,2-difluoroethane, the most stable conformation of which is Gauss conformation, in which CH sigma bonding orbital on one carbon is parallel to the CF sigma antibonding orbital on the other. This allows the transfer of CH sigma bond pair to vacant sigma star of CF to produce the hyperconjugative structures like this. Now we will discuss hyperconjugation from the molecular orbital point of view. Let's first take ethyl carbocation, which can be drawn in perspective formula like this. This is the vacant p orbital of positively charged carbon atom. This is the CH sigma bond of sp3 hybridized carbon parallel to the vacant p orbital. The molecular orbital of this bond can be shown like as. These are the two bond pair electrons of the sigma bond. Overlap of CH sigma bond with vacant p orbital causing breaking up CH sigma bond to generate a proton, formation of a pi bond, and transfer of the bond pair to the pi bond. Now let's have second example, propene, which can be drawn in perspective formula like as. This is the vacant pi star. For the sake of simplicity, pi orbital has not been shown. This is the CH sigma bond parallel to pi star, the molecular orbital of which can be drawn like as. This is the sigma bond electron pair. Overlap of CH sigma orbital with pi star causes breaking up CH sigma bond, formation of pi bond between right side carbon and middle carbon, and at the same time delocalization of these pi electrons to left side carbon where it stays as a lone pair. So this will be the skeleton of hyperconjugative structures. These are the pi orbitals and orbital with lone pair. So 2 electrons will be in pi orbital and 2 as a lone pair in this orbital. 1,2-difluoroethane. We know that the most stable conformation of 1,2-difluoroethane is Gauss, which can be drawn in perspective formula like as. In this conformation, one of the two CH sigma bonds of one carbon is parallel to the antibonding of CF sigma bond of the other carbon. So, in this conformation, overlap of bonding orbital of the CH sigma bond with antibonding orbital of CF sigma bond allows the transfer of CH sigma electron pair to antibonding CF sigma bond. Because of this, CF sigma bond is broken and a pi bond is formed between two carbon atoms. Thus, we can draw the hyperconjugative structure like as. Negative or reverse hyperconjugation. In negative hyperconjugation, there is donation of electrons from filled pi orbital or non-bonding orbital to the sigma star orbital, resulting in building pi character into bonds that normally possesses only sigma character. The first example which we are going to take is fluoromethylamine. The most stable conformation of this molecule has been found to be the conformation in which the orientation of CF bond is anti-parallel to the nitrogen lone pair. This is because of favorable negative hyperconjugation in this conformation, which allows the donation of lone pair on nitrogen to sigma star orbital of CF sigma bond that results the formation of CN pi bond and breaking up CF sigma bond and thus leading to the formation of this hyperconjugative structure. This results in shortening of CN bond, lengthening of CF bond, and an increase of the angle around carbon and nitrogen. Second example is 3,3,3 trifluoropropene. In this example, the sigma bond on sp3 carbon between carbon and fluorine cannot donate electron pair to adjacent pi star due to higher electronegativity of fluorine atom. Here, the electrons from the filled pi orbital are donated to the sigma star of CF sigma bond, resulting in pi bond formation between middle carbon and the carbon bearing fluorine and breaking up CF bond to generate this hyperconjugative structure. Similarly, breaking up the other two CF sigma bonds can produce two more hyperconjugative structures. Trifluoromethylbenzene. In this example also, because of higher electronegativity of fluorine atom, CF3 carbon becomes electron deficient. Donation of pi electrons from the adjacent pi bond to the sigma star of one of the three CF bonds results in generation of positive charge at ortho position, formation of a pi bond between CF3 carbon and ipso carbon, and breaking up CF bond generates this hyperconjugative structure. This pi bond can delocalize to give another structure. Delocalization of this pi bond can give one more structure. Similarly, breaking up sigma bond with pink colored fluorine atom can give these three hyperconjugative structures, and breaking up sigma bond with green fluorine atoms can give these three more structures. From these hyperconjugative structures, we can see that ortho and para positions are electron deficient. Therefore, CF3 is a meta-directing for aromatic electrophilic substitution reaction. Negative hyperconjugation in anomeric effect. In the case of tetrahydropyrene bearing an electronegative substituent at position 2, which is also called anomeric carbon, the substituent prefers axial position. Thus, in this case, chair conformation with axial substituent is more stable than the chair conformation with equatorial, despite there is presence of 1,3 diaxial interaction in chair conformation with axial substituent. The tendency of heteroatomic substituents at the anomeric carbon to prefer the axial orientation instead of less hindered equatorial orientation is called anomeric effect. The most accepted explanation for the anomeric effect is that the ring oxygen has two lone pairs in the non-bonding orbitals. Out of two, one is axial and another equatorial. The chair conformation with axial substituent, the anti-bonding orbital of CX sigma bond is parallel to the axial non-bonding orbital. Because of this, there is overlap between axial non-bonding orbital of oxygen and anti-bonding orbital of CX sigma star. This stabilizing interaction is stronger than the destabilizing 1,3 diaxial interaction, and as a result, the chair conformation with axial substituent becomes more stable. If we look at the chair conformation with the equatorial substituent, This is Cx sigma star, which is not aligned for the overlap with the non-bonding orbital of the ring oxygen. Significance of hyperconjugation. There are several facts which can be explained by hyperconjugation. The first is stability of carbocation. We have seen that the hyperconjugation delocalizes positive charge of carbocation and thus increase the stability. So, the greater the number of hyperconjugative structures, higher will be the stability of carbocation. For example, among methyl, ethyl, isopropyl and tert-butyl carbocations, the number of hyperconjugative structures is 0, 3, 6 and 9 respectively, as they have 0, 3, 6 and 9 alpha hydrogens. If we talk about stability order, methyl having no hyperconjugative structure is the least stable. Ethyl carbocation with 3 alpha hydrogens is more stable than methyl. Isopropyl carbocation with 6 alpha hydrogens is more stable than ethyl, and the tert-butyl carbocation with 9 alpha hydrogens is the most stable among these. Stability of carbon radicals. Similar to the carbocation, stability of carbon radicals increases with the increasing number of hyperconjugative structures. Thus, among methyl, ethyl, isopropyl and tert-butyl radicals, methyl is the least stable, ethyl is more stable than methyl, isopropyl is more stable than ethyl, and tert-butyl is the most stable. Stability of alkenes. We have seen that the hyperconjugation delocalizes pi electrons of alkenes and thus increases the stability. So, the greater the number of hyperconjugative structures, higher will be the stability of alkene. For example, among ethene, propene, 2-butene, 2-methyl-2-butene and 2,3-dimethyl-2-butene, the number of hyperconjugative structures is 0, 3, 6, 9 and 12 respectively, as they have 0, 3, 6, 9 and 12 alpha hydrogens. If we talk about stability order, ethene having no hyperconjugative structure is the least stable. Propene with 3 alpha hydrogens is more stable than ethene. 2-butene with 6 alpha hydrogens is more stable than propene. 2-methyl-2-butene with 9 alpha hydrogen is more stable than 2-butene, and 2,3-dimethyl-2-butene with 12 alpha hydrogens is the most stable among these. Thus, we can generalize that the stability of alkenes increases with the increasing number of alkyl substituents. Explanation of Baker and Nathan effect. Alkyl groups are electron donating in nature. The electron donating tendency of methyl, ethyl, isopropyl and tert-butyl groups by inductive effect follows the order. Methyl is the least electron donating. Ethyl is more electron donating than methyl. Isopropyl is more electron donating than ethyl, and tert-butyl being the most electron donating. This order is reversed when they are attached to unsaturated system. This is called Baker and Nathan effect. Baker and Nathan studied the kinetics of reactions of pyridine with para-substituted benzyl bromides in acetone at 40 degrees centigrade to produce pyridinium salt. The rate of reaction is accelerated by electron donating group R. The relative rate constant Kr upon Kh for R is equal to methyl, ethyl, isopropyl and tert-butyl was found to be 1.66, 1.40, 1.35 and 1.34 respectively. This suggests that as we move down the table from methyl to tert-butyl through ethyl and isopropyl, the electron donating tendency decreases, which is reverse of the normal order. This order was explained based on hyperconjugation. Here we can see that 4-methyl benzyl bromide, 4-ethyl benzyl bromide, 4-isopropyl benzyl bromide and 4-tert-butyl benzyl bromide respectively have 3, 2, 1 and 0 hydrogens for hyperconjugation. So methyl having highest number of hydrogens for hyperconjugation is the strongest electron donor, and tert-butyl with no hydrogen for hyperconjugation is the least donor. Explanation of anomeric effect. We have already gone through the anomeric effect in detail, so I am not going to discuss it again. Hyperconjugation is considered to be the better explanation for anomeric effect. Explanation of conformational stability. The most stable conformation of many compounds can be explained in terms of hyperconjugation. For example, the most stable conformation of ethane is staggered and the most stable conformation of 1,2-difluoroethane is Gauss. These can be explained by hyperconjugation. I am not going to get into details as I have made separate videos on these topics. You can find the link for them in the description box of this video. That's all in this video. Please subscribe my channel and press the bell icon if you like this video. Thank you very much for watching this video.